Hello, my name is Thomas Anderson, and this is a continuation of the Equilibrium project for 4U chemistry. So, in the last video, I discussed the equilibrium of hydroxylapatite, which is essentially this molecule that rests in your enamel, and it rests in equilibrium with its dissociated form of itself. And essentially, whenever there's an acid that interacts with this molecule, it causes a shift into the ionic forms, which deteriorates the solid form of the hydroxylapatite, which is what protects your teeth, causes decay, not fun. This isn't the only example, as it turns out, of an equilibrium system within our bodies that help keep us healthy. So, today we're going to be discussing hemoglobin. Now, this is the equilibrium of hemoglobin in particular. Hemoglobin is the molecule often shown as a little red blood cell in our body, and it's referred to as red blood cell from time to time because that's essentially what it is. It's a large part of it anyways. It's a protein within our red blood cell that contains iron, which is what causes what allows the oxygen to bind to it. But that's not important. All we need to know is this simple equation right here. So, the hemoglobin will bond with oxygen whenever we breathe in. This happens in our lungs right here, this process of it. Breathe in, and then the oxygen will bind with the hemoglobin and then become oxygenated. And since there's less oxygen within our muscles, what will happen, since the partial pressure of oxygen is less in our muscles, there'll be an equilibrium where this will want to go distribute. The oxygen will want to distribute itself to the lesser oxygenated muscles. And this is very important. This is in constant equilibrium. A great example of where this comes into play, scuba divers. They will dive down to the bottom of the ocean, come back up, take some photo of some cool fishes and some fishes that I wish I haven't seen because they still haunt my dreams. But it's a very, very important system that interacts with the oxygen they breathe in here. So basically what happens, oftentimes you'll hear about scuba divers, how they essentially have to dive at a controlled rate. Now, why is this? Why can't they just dive straight down there? Well, that's because as they dive down, there's a change in pressure in the water. So that's all good and well, but what does that mean for us? Well, essentially, that change in pressure affects this side of the equation. The pressure sucks in. As the pressure increases, the oxygen is more dense, and this creates further binding and a shift to the other side due to Le Chatelier's principle. If there's more pressure here, it's going to shift to the other side, and that causes more oxygenated blood. Now, if this happens too quickly before this oxygen can be distributed in time or effectively at all, what will happen is you'll get oxygen poisoning. That's not very fun. You don't want that. So that's why scuba divers go down really quickly. For converse reasons, and this is why this is a great example because it shows how this works in reverse. If they're coming up, if the pressure is decreasing here in your lungs, if it's decreasing, opening up, well, this is going to suck some oxygen from the hemoglobin here. It's going to want to shift back and cause more oxygen and more hemoglobin separately, right? So basically, that's why oftentimes you'll hear about people basically oversimplifying it, saying, well, if you come too fast, if the pressure in the air decreases too quickly, what'll happen is your blood will explode. Which it sounds kind of dramatic, but it isn't actually far from the truth, because what'll happen here, there'll be such little oxygen and hemoglobin here, and it'll want to shift there so bad that the oxygen will essentially burst out of the hemoglobin, and that causes your blood to quote-unquote boil or explode, or fancy TV terminologies that you'll see on a cool episode of some science show on HBO or whatever. And that's what people know as like boiling or exploding blood. So that's very cool. The same concept applies to mountain climbers who go up really high altitudes, higher pressure. Same things happen, but sort of in reverse, because that's the way the atmosphere works. Another really important part of blood is this guy. This is our blood buffer. This helps maintain pH in our blood. which is an important equilibrium system, and thank God for it. So essentially, this serves to make it so that if our blood is too acidic, it'll shift one way or the other. Let me explain here. So this is carbon dioxide. This is water. This is our carbonic acid, hydrogen ion, and finally, bicarbonate ion, I believe. So what'll happen here, say our pH is too high, too many hydrogens. Okay, great. Bicarbonate ion bonds with this, shifts this way due to Le Chatelier's principle. Too much here, it'll shift over here, and then it'll shift over here. Furthermore, if there's not enough water or CO2 in our blood, so it sort of acts as a little reserve, this guy, for also these things. But in reality, this is a very weak acid. Now that means it's going to want to disassociate more rapidly. So this carbonic acid in the middle, it actually isn't as prevalent as these guys. So that's why these guys exist. They're sort of like, carbonic acid is almost like a transitionary state between these guys and these guys. It sort of passes the baton of the hydrogen and the oxygen and, all the important molecules that help us live. Conversely, let's say we don't have enough of this. We don't have enough hydrogen in our blood. The opposite will happen. Carbon dioxide will bond with water, carbonic acid, temporarily, boom, disassociates and creates that H+ ion with the bicarbonate ion. So this is super duper 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 important. I don't know if you've ever had too much acid in your blood, but it's not fun. Basically, our blood maintains a pH smack dab in the middle of the spectrum, which means that it's about, I believe it's 7.4 to 7.6. And that's very important. You want your blood to be right there, happy and healthy in the middle. So those are two amazing ways that our blood, in particular, helps keep us healthy and helps keep our bodies regulated, thanks to all the various equilibriums that are found within it. So yeah, thank you very much for listening, and I hope you enjoyed. You probably didn't learn anything since this is for a teacher and it's demonstrating my knowledge, but I hope you learned that my knowledge is good enough for full marks, hopefully. If you don't give me full marks, I'm going to remove the equilibrium systems from your blood, and you don't want that. So yeah, goodbye.